Hello everyone, and welcome back to some more remote learning. In today's video, we're eventually going to get into logarithmic differentiation. But before diving into this worksheet, I highly recommend you review your logs and exponents rules because they're going to come up a lot in these worksheets and be helpful when solving. So go ahead and take a few minutes to review those rules, and then we'll jump into this worksheet. So now that you've hopefully reviewed those rules on your own, or reviewed them using one of my other videos, let's dive into the derivative of the natural log. So we already know how to find the derivative of y equals e to the x. Remember, the derivative of y equals e to the x, that dy dx is equal to e to the x. The derivative of e to the x is e to the x. So we're going to use this information to find the derivative of y equals the ln of x. So if y equals the ln of x, I don't really know how to take the derivative of ln of x yet. That's what we're learning. But I know how to take the derivative of e raised to something. So what I'm going to do is I'm going to raise y equals ln of x. I'm going to raise that left-hand side from e and my right-hand side. So I'm going to have the base of e for both sides of my equation. E to the y equals e to the ln of x. And again, why I said to review your log rules is because this e to the ln, because those are inverses, they essentially will cancel each other out. So I'll get that e to the y equals x. And we know how to take the derivative now implicitly. So how do we take the derivative of this with respect to x? Well, the derivative with respect to x of e to the y is going to be equal to the derivative with respect to x of x. The derivative of e to the y is going to be e to the y times dy dx. Because remember, y is that function of x, so we need to use the chain rule. So e to the y dy dx is going to be equal to, what's the derivative of x? That's 1. So when solving for that derivative, we get that the derivative of y with respect to x is going to be equal to 1 over e to the y. And I did that by dividing both sides to isolate that dy dx. So we have 1 over e to the y. Our derivative is now in terms of y, but I really want it in terms of x. And I can see that e to the y is, well, e to the y is x. We have this relationship. E to the y is x, so my derivative is equal to 1 over x. So the derivative of the ln of x is 1 over x. So let's use this same thought process now to find the derivative of the ln of 3x squared plus 2x. So again, we know how to take the derivative now of ln of x, but how does the chain rule really work? We do the derivative of the outermost function and work our way to that innermost function. But let's pretend we didn't really know the chain rule quite yet. How would we find that derivative? Well, again, I'm going to take everything to a base of e. So I'm going to have e to the y equals e to the ln of 3x squared plus 2x. Remember, e and the ln function are inverses of each other, so I'm going to get e to the y equals 3x squared plus 2x. Now I can easily take the derivative of each side, remembering that implicit differentiation. So I'm going to take the derivative of e to the y with respect to x, and I'm going to take the derivative of 3x squared plus 2x with respect to x. The derivative of e to the y, remembering that chain rule because y is a function of x, it's going to be e to the y times y prime, or e to the y times dy dx. And that's going to be equivalent to the derivative of 3x squared plus 2, which is 6x plus 2. So to solve for that derivative, dy dx, isolating it, I divide everything by e to the y. So I'll have 6x plus 2 all over e to the y. But what is e to the y? E to the y is that 3x squared plus 2x. So my derivative, just in terms of x, is going to be 6x plus 2 all over 3x squared plus 2x. Now let's think about this as far as the chain rule goes. Remember, if we're taking the chain rule, we take the derivative of that outermost function and then multiply by the derivative of the innermost function. Our derivative of our outermost function, the ln of x, is 1 over x. So if we have to take the derivative with respect to x of the ln of some function f of x, well, that derivative is, what's the derivative of ln of x? That's 1 over x. So we'll have 1 over our function, and then we multiply that by the derivative of that innermost function times f prime of x. So the derivative, making this a little bit neater so you can read it, I'm going ahead and put brackets around it so it's not so many parentheses. The derivative of the ln of f of x, that derivative with respect to x is going to equal 1 over f of x times f prime of x, or just f prime of x over f of x, which from directly up above we can see. The ln of f of x, we've got 1 over f of x times f prime of x. F prime of x over f of x, where the f of x was our 3x squared plus 2x. So now that we've got a good introduction on taking the derivative of that natural log function, let's calculate the derivatives of each of the following. Zooming on in, for example 1, we're going to be taking the derivative of the ln of 4x. dy dx is going to be equal to, remember that chain rule, 1 over f of x, so 1 over 4x times the derivative of f of x, the derivative of 4x, which is 4. This simplifies nicely because our 4's will cancel out. So the derivative of ln of 4x becomes 1 over x. And here's a neat trick. Let's use a log rule so we don't have to use the chain rule. What's another way I can rewrite the ln of 4x? I could have wrote it as the ln of 4 plus the ln of x, because remember, when I have my logs, if I have something multiply within my log, I can split it up as addition. What's the derivative of ln of 4? The ln of 4 is just a constant and goes to 0. What's the derivative of ln of x? 1 over x. There we go. So the chain rule wasn't even necessary with that if we would have used a log rule first. Let's move on to part B. In part B, we have x squared times the ln of 6x. We have some function times another function. That's going to be the product rule. And remember, for product rule, if you need to, feel free to bookkeep, especially since we're just now learning these logarithmic functions and their derivatives. However, I'm just going to talk through it, but feel free to write that bookkeeping method down. So f prime of x is going to equal our first function, which is x squared, times the derivative of the second, and I'm going to write out the derivative of the second, plus our second function, times the derivative of our first. And I wrote out taking those derivatives so that I'll do that in my next step, since we're still just practicing. So I'm going to have x squared times, what's the derivative of ln of 6x? Well, if you remember from ln of 4x up above, we can either split that up or we can use the chain rule, but regardless, that 6 is going to get canceled out in the chain rule, or it's going to go to 0 when we split it up. So this becomes 1 over x, and then I'll add that to the ln of 6x, all multiplied by the derivative of x squared, which is 2x. Simplifying this down, x squared over x becomes x, so I have x plus 2x times the ln of 6x. And that's my derivative for part B. In part C, now I'm going to be using not the product rule, but the quotient rule. Low d high minus high d low all over low squared. And in this case, I threw in the variable t just to give us practice with envisioning things not necessarily as an x, but we're still just taking the derivative with respect to t. So we're going to have f prime of t equals low sine of t times the derivative of our high. What's the derivative of ln of t? That's 1 over t minus high, that's the ln of t, times the derivative of our lower function. What's the derivative of sine of t? That's going to be a positive cosine of t, and that's all over our denominator squared, the sine of t, that quantity squared, or sine squared of t. And just like that, we've calculated the derivative. Sine of t over t minus ln of t times cosine of t all over the sine of t, that entire quantity squared, or sine squared of t. Now in part D, just like in part A, we can do this one of two ways. Because we have multiplication, we can split up the logarithmic function and take the derivatives, or we can take the derivative using the chain rule. I'm going to do both just for practice. So I'm going to start by, let's go ahead and start with the chain rule. So we'll have dy dx equals, remember, outermost function first. That is going to be the ln of our inner function. And the ln of some function is going to be 1 over that function. So I'm going to have 1 all over 3x to the fourth plus 1 times 4x squared minus 5. And then I multiply that by f prime of x, multiplied by the derivative. And that derivative is also going to require a little bit of product rule. So I'm going to, as opposed to multiplying, I'm just going to write this right up on top in the numerator. I'm going to have my first function, which is 3x to the fourth plus 1, times the derivative of the second, which is going to be 8x, plus second, which is going to be 4x squared minus 5, times the derivative of my first, which is going to be 12x cubed. Now what I want to note is that this is actually going to look a little bit neater if we split this fraction up. Because when I split my fraction up, I'll have 3x to the fourth plus 1 times 8x all over that common denominator of 3x to the fourth plus 1 times 4x squared minus 5. And then I'll be adding that to, well, we have that same denominator of 3x to the fourth plus 1, or 4x squared minus 5. And I'm going to have my numerator at this term is 4x squared minus 5 times 12x cubed. And look what happens. My 3x to the fourth plus 1 cancels out, and my 4x squared minus 5 cancels out. So leave me with 8x over 4x squared minus 5 plus 12x cubed over 3x to the fourth plus 1. And let's go ahead and double check this by splitting up the log. So splitting up our logarithmic function first, I'm going to take the derivative of the ln of 3x to the fourth plus 1 plus the ln of 4x squared minus 5. Taking the derivative of each of those individually, because there's addition in between, I'll apply the sum rule. So starting with that first ln function, I'm going to have 1 over 3x to the fourth plus 1, and then I multiply by that inside by the derivative of 3x to the fourth plus 1, which is 12x cubed. And then I'm going to add that to my other derivative, starting with the outermost function, that ln. It's 1 over that function times the derivative of the function. So I'm going to have 1 over 4x squared minus 5 times the derivative of 4x squared minus 5, which is 8x. And there we have it. There's my 12x cubed over 3x to the fourth plus 1 plus 8x over 4x squared minus 5. There's my 8x over 4x squared minus 5 plus my 12x cubed over 3x to the fourth plus 1. So sometimes remembering those log rules makes it a lot less work when taking the derivative. That's why I said it was important in the beginning to review those. Now let's move on from logarithmic functions to exponential functions. How would we calculate the derivative of y equals b to the x? So let's think about how to calculate this. It's this x in my exponent that's giving me an issue. I know how to take the derivative when I can apply the power rule, having x raised to some constant, but I don't know how to take the derivative when I have some constant raised to the x. But remember what I said at the beginning of this worksheet about using different log rules. How do we move something out of an exponent? We can take the ln of it. So I can take the ln of b to the x and get x times the ln of b. However, this has an issue now because if I take the ln of the right-hand side of my equation, I also have to take the ln of the left-hand side of my equation, which is going to be helpful when we get into logarithmic differentiation. But for now, with just some constant to the x, what are we going to do? Well, remember the inverse of the ln function is e to the x, right? So I can keep this the same, still taking the ln, but I'm just going to do e to the ln of b to the x. Remember, e to the ln, that cancels out, so I still technically have my y equals b to the x. I've just manipulated a bit, because now I can pull that exponent of x down in front. So I can have y equals e to the x times the ln of b. And we know how to take the derivative of this, right? What's the derivative of e to the x ln of b? dy dx is going to be, well, e to some function times the derivative of that function. So e to the x ln of b times the derivative of x ln of b. What's the derivative of x ln of b? You might be thinking product rule, but we don't have to use the product rule because b is just a number. So the ln of b is some constant times x. Constant multiple rule, that's just going to be multiplied by the ln of b. So here is my e to the f of x times f prime of x, and e to the f of x is really what? Well, remember e to the x ln of b is e to the ln of b to the x, which is just b to the x. So the derivative of y with respect to x is b to the x times the ln of b. And this is the case when b is just some constant. So now that we know this formula, let's look below. 6 to the x, how would we take that derivative? Well, b to the x times the ln of b, the derivative of y with respect to x is just going to be 6 to the x times the ln of 6. B to the x times the ln of b. Let's move on to part b. How would we take the derivative of f of x if we have 5 to the x over 3? All right, so we don't just have some constant raised to the x, we have some constant raised to x times 1/3. So if I want to rewrite this as 5 1/3 x, maybe that's a little bit easier to see. Well, remember, e to the ln of b to the x is still just b to the x. So I could write this as f of x equals e to the ln of 5 to the x over 3, or 5 to the 1/3 x, where I can bring that exponent down in front when I take the ln. So this becomes e to the 1/3 x times ln of 5. What's that derivative? That's e to the function times the derivative of the function. So e to that 1/3 x times ln of 5, all multiplied by the derivative of that, constant multiple rule. The derivative of 1/3 times x times the ln of 5 is just going to be 1/3 ln of 5, or ln of 5 all over 3. So this becomes, remember what was this? This we started out as 5 to the x over 3. So we have 5 to the x over 3, all multiplied by the ln of 5, and that's all over 3. So you can see that part b was a little bit trickier, but that same kind of formula still applied. B to the x times the ln of b, but we had to finish out that derivative because x was multiplied by some constant. We had to take that into account when doing our derivative. Now that we've got some good practice in, it's time to really dive into some logarithmic differentiation. Now that we understand how to take the derivative of a logarithmic and exponential functions, we will use that information to help us calculate the derivatives of functions raised to another function. So not just some constant raised to the x, but maybe like 3x squared raised to the x. Or like in part A, x to the sine of x. How do we do that? Well, the method we're going to use is called logarithmic differentiation. So we're going to evaluate the derivative of each of the following using that method. And the key for logarithmic differentiation is that we're going to take the ln of both sides. So if I take the ln of both sides, I'll have the ln of y equals the ln of x to the sine of x. Now, when I take the ln of both sides, on that right-hand side, it allows me to bring that exponent down in front. So this step should be fairly familiar from directly up above. So simplifying this down, we're going to have the ln of y equals sine of x times the ln of x. Now we're going to take the derivative. But because we have some function, not just y by itself, on that left-hand side, we're going to need to use implicit differentiation. So what's the derivative of the ln of y? Remembering that chain rule, it's going to be 1 over y times the derivative of y. So times dy dx. And that's going to be equal to, what do we have here? A little bit of product rule. So we're going to have first sine of x times the derivative of the second, which is 1 over x, plus second, the ln of x, times the derivative of the first. The derivative of sine of x is cosine of x. So simplifying this down and solving for that derivative function, we have dy dx equals sine of x all over x plus the ln of x times cosine of x, and this is all multiplied by what? By y. We're multiplying both sides by y in order to cancel it out from my left-hand side. That was when I isolated my dy dx. But I don't want y in my problem if I know what y is. Remember, y was given to us at the start. Y is x to the sine of x. So my derivative is x to the sine of x. There's my y, all multiplied by the sine of x over x plus the ln of x times cosine of x. And that's my derivative in part A. So you can see it's kind of similar to the b dx times the ln of b, except we didn't have that constant to deal with, so we had to do a little bit of product rule. And we could have done the same exact problem using the steps up above. We could have taken the ln of our right-hand side and also left it as a base of e. So we could have still left this as y equals e to the ln of x to the sine of x, where we pull that sine of x right on down in front, but we're going to get the same result. Because remember, e to some function is e to that function times the derivative of the function. So when I pull that sine of x down in front, you can see that I'll have e to the sine of x times ln of x. If sine of x, ln of x is my f of x, there we have it. We have e to the f of x times our f prime of x when we take the derivative. Here is my f prime of x, and there is my e to the f of x. That is my y, just the manipulated version of it. But in my opinion, logarithmic differentiation is a little bit easier because you won't have to have so many exponents in your problem. You'll just have the ln of y equals the ln of that original function. But let's move on to part B. In part B, I switch up my variable to be in r, but the same rules still apply. When we take the derivative f prime of r, we need to somehow get that exponent out of there. And how we do that, we take the ln of both sides. So I'm going to have the ln of f of r is going to be equal to the ln of r to the r squared plus 3r. Now that I've taken the ln of that, let's go ahead and simplify it down before we begin the derivative. So we have the ln of f of r is going to be equal to r squared plus 3r. That is all multiplied by the ln of r. Now you can see I can take the derivative of both sides easily. Taking the derivative of my left-hand side, d dr, that's going to be 1 over f of r times f prime of r. Remembering that chain rule, 1 over the function times the derivative of the function. That's how I take the derivative of the ln of some function. And then product rule on my right-hand side, I'll have first r squared plus 3r times the derivative of the second, 1 over r, plus second, that's the ln of r, times the derivative of the first, that's going to be 2r plus 3. So there's that product rule. I just need to simplify this down and solve for f prime of r, And in order to do that, I'm going to multiply by f of r on both sides to cancel it out from my left-hand side. And remember, f of r is that original function that gets multiplied to everything. So writing this out, I'm going to have f prime of r equals, I'm going to write my f of r first. That's going to be my r to the r squared plus 3r, and I'll put that in parentheses so you can see that is my exponent, and that gets all multiplied by r squared plus 3r over r plus 2r plus 3, that quantity, times the ln of r. And there we have it. That's my derivative in part B. And you can simplify this down using log rules if you want to move that 2r plus 3 up into the exponent of r within that logarithmic function that's left within your problem. But I'm going to leave it as is and continue on. In part C, we have g of x equals the cosine of x cubed all raised to the x. How are we going to solve for this? Logarithmic differentiation. So we're going to take the ln of both sides. So we're going to have the ln of g of x. And now that we've got familiar with why we're taking the ln, I'm going to go ahead and pull my exponent down in front in this step. So I'm going to have x ln of cosine of x cubed. Now we're ready to take the derivative because we have product rule on the right and just a simple chain rule on the left. So the derivative of the ln of g of x is going to be g prime of x all over g of x, and that's equal to a little bit of product rule. First times the derivative of the second. The derivative of the ln of cosine of x cubed is going to be a chain rule. So I'm going to have 1 over that function, so 1 over the cosine of x cubed, that's 1 over that inner function, times the derivative of that inner function, which is still a little bit more of a chain rule. What's the derivative of the cosine function? That's going to be a negative sign. So this gets multiplied by a negative sine of x cubed, but I'm not even all the way to my innermost function yet. That very innermost function is that x cubed. So then I multiply by 3x squared. If you're confused on this part, taking the derivative using the chain rule, please refer back to the chain rule example worksheet where we go over quite a few chain rule examples doing functions within functions within functions. So refer back to that if you need a refresher. But for now, I have first times the derivative of the second, and then I'm going to add that to second, which is the ln of cosine of x cubed, times the derivative of the first. What's the derivative of x? That's simply 1. So there is my product rule. Now in order to solve for g prime of x, what do? I multiply both sides by g of x. But what is g of x? G of x is just that original. So I'm going to have the cosine, and I'll go ahead and write my final answer in a different color. G prime of x, I'm going to have the cosine of x cubed, that all raised to the x. And that got multiplied by doing that product rule as the derivative. Simplifying this down, x times 3x squared is going to be 3x cubed, and I have that negative out in front, so I'll have a negative 3x cubed times sine of x cubed all over cosine of x cubed, which I can even simplify this down. Sine over cosine, that's just tangent. So I'm going to have negative 3x cubed times tangent of x cubed, because I had a sine of x cubed over a cosine of x cubed, and then I'm going to add that to, can't really simplify this down any, but multiplying by 1 leaves it as is, so the ln of the cosine of x cubed, and making sure I include that parenthesis because my original function should be multiplied by that simplified product rule. And there we have it. That's my derivative in part C. Let's move on to part D. In part D, this looks like just a simple quotient rule. However, I asked you to use logarithmic differentiation. So when we take the ln of both sides, it actually might make this a little bit easier, because when we take the ln of both sides, I'll have the ln of y equals the ln of some quotient. We can split that up using log rules into subtraction. So I'm going to have the ln of y equals the ln of the cosine of x, that entire quantity to the fourth, minus the ln of 4x minus 5, that quantity raised to the third. Now, let's take the derivatives. The derivative of ln of y is 1 over y times dy dx, remembering that chain rule, and the derivative of the ln of cosine of x, all raised to the fourth, again a chain rule. We have 1 over the function, so 1 over cosine of x raised to that power of 4, but then we multiply by that next derivative, which is actually the cosine of x raised to the fourth, so that's 4 cosine cubed of x, and then the derivative of that next function is just the cosine of x, and the derivative of cosine of x is a negative sine of x, and we don't need to go further because the derivative of x is just 1. So we have that, and then we're subtracting it from, well, again, we have a little bit of chain rule here, or if we want to apply the log rule at the start, we can pull that 3 right on down in front. The derivative of 3, ln of 4x minus 5, is going to be 3 over 4x minus 5, all multiplied by the derivative of 4x minus 5, which is just 4. And just to show you quickly that it didn't matter whether we dropped the exponent down in front at the start or not, if we didn't, then that derivative would have become 1 over 4x minus 5, all raised to the power of 3, so that's 1 over f of x, but we have to still multiply by that derivative, which in itself is the chain rule. So we're going to drop that exponent of 3 down in front, have 4x minus 5 now squared when we decrease that exponent by 1, but we still have to multiply by the derivative of the inside, which is 4. Look what happens. 4x minus 5 squared cancels out with 2 of my 4x minus 5's in my denominator to leave me with 4x minus 5 to the first, and then my 3 times 4 is still there. So 3 times 4 over 4x minus 5. Now what do I have to do? I have to multiply everything by y in order to solve for dy dx. So dy dx is going to equal y, which is my original function. Cosine to the fourth of x over 4x minus 5 cubed. That is my y, and that all gets multiplied by this entire derivative. And I can simplify down as I go along, because cosine cubed of x will cancel out to leave me with cosine of x in my denominator, and sine over cosine is the tangent. So I'll have negative 4 tangent of x, and again, that's because I have this 4 remaining, and a negative sine of x over cosine of x is going to be a negative tangent of x. So I got negative 4 tangent of x minus 12 over 4x minus 5. And there we have it, making sure that y, that original function, was multiplied by the derivative of that right-hand side of my equation, cosine of x to the power of 4 over 4x minus 5 cubed, all multiplied by negative 4 tangent of x minus 12 over 4x minus 5. And that pretty much wraps up our examples in this worksheet, but I want to consolidate and write down the important derivatives in this important notes section so that if you're using this as a reference, you can just go back to this to look up your information. One note is that the derivative of the ln of x was equal to 1 over x. That's what we started with. That was one of our first derivatives we did. The next derivative we talked about was the derivative of b to the x. And if you remember, that was b to the x times the ln of b. Now for the other parts we did logarithmic differentiation, or we had to do a little bit of chain rule. But let's assume that we're taking the derivative of some function that isn't necessarily a natural log function. Let's say we're trying to take the derivative with respect to x of, let's do some log base b of x. Well, what's that derivative? Let's talk about it really quickly, and then I'll put it in the notes. Log base b of x, we can rewrite this again using log rules. If y equals log base b of x, that means that x equals b to the y. And we can take the derivative of this with respect to x, right? The derivative with respect to x of our left-hand side is 1, and the derivative with respect to x of our right-hand side, think about it, b to the x times the ln of b, but I have some function that's going to be b to the y times the ln of b times the derivative of y with respect to x, because I had to remember that y is some function of x. So simplifying this down, solving for dy dx, that's just going to be, writing this back up for my log derivative, 1 over b to the y times the ln of b. But what was b to the y? B to the y was x. So this is 1 over x ln of b. And that's the derivative of log with a different base, which makes sense because remember, log base e is that ln. So if we have the log base b of x, that's the same as the ln of x. If we were to plug that into this formula here, that would be 1 over x ln of e, which the ln of e is 1, to leave us with 1 over x. So there we have it. That's just some important information consolidated down for taking the derivatives, helpful rules to speed the process up. So if you have any questions, please feel free to reach out and let me know. And don't forget to pull more problems from the book or an online resource to continue to practice logarithmic differentiation and the derivatives of logarithmic and exponential functions. And then continue on to the next video. But until then, good luck with your online learning.